Hello dear friends, in this video we will discuss our ability to simulate multi-stream plate fin heat exchangers in the Aspen EDR software. According to the schematic, this sample exchanger has 3 streams including 2 hot streams and 1 cold stream. The flow composition is also clearly defined here. Compositions include well-known hydrocarbons. Pressures are also specified. The mass flow rates of the streams are also specified here. Inlet and outlet temperatures are also specified. Now everything is ready for simulation by the Aspen EDR software. Okay, now we enter the Aspen EDR software and click on New. From the various modules, we select the plate fin module. Okay, we have entered the plate fin exchanger simulation section. Now we click on Design. Note that we want to design the exchanger from scratch. Okay, in the data process section, we only see 2 streams, while we need 3 streams. To do this, we enter the data application section and select 3 for the number of streams. Now to select variable units in the units set section, we select SI units. By doing this, our desired units such as pressure are selected. In the first step, and to determine the composition of stream 1, we select the ComThermo library. According to the problem statement, compositions are in molar fractions. Therefore, in this section, we select molar flow rate or molar percent. We click on Search Data Bank and select ethane, propane, and isobutane. According to the problem statement, we enter the mole percentage. After selecting the components and their molar ratios, we need to select the Peng-Robinson state equation. Okay, the composition of stream 1 is specified. Now we move on to stream 2. Streams 2 and 3 have similar compositions including ethane and propane. Now, similar to stream 1, for stream 2, we select the ComThermo library and specify the molar flow. In the data bank search section, we also select ethane and propane and enter the percentage as stated in the problem. Here too, we select the Peng-Robinson equation for the state. For stream 3, we follow exactly the same procedure as for stream 2. Just pay attention to selecting the mole flow option. Note that these items vary depending on each project. Okay, we also select Peng-Robinson here. Okay, now after specifying the compositions, we return to the data process section. First, we enter the mass flow rates of the streams according to the problem statement. Note that the parameter units are exactly the same as the problem statement, which is kilograms per hour here. Now it's time to determine the pressures according to the problem statement, which are 10, 5, and 10 bar respectively. Note that by specifying the pressures, the software assumes a pressure drop. In fact, this is an approximation, and if pressure drop is important for our project, a special attention is needed here. Now we also need to specify the inlet and outlet temperatures of the streams. Here for stream 1, it goes from positive 25 to negative 25 degrees Celsius. Stream 2 enters at negative 70 degrees Celsius and exits at 0 degrees Celsius. Stream 3, which is the hottest stream, is cooled from 25 degrees to negative 47 degrees Celsius. Okay, with all the necessary items specified, the software is ready for initial design. Now by hitting run, we have to wait for the simulation to finish, which will take some time. Note that no mandatory parts are left empty and we can hit run. Note that depending on the complexity of the problem and the processing system's speed, the problem-solving process may take time. Great! As you can see, we have no errors or warnings from the software. In fact, we only have some notes and no errors, indicating the correct solution of the problem. Okay, in the results section, we enter the thermal performance section to examine the solved results. We select the heat load unit as kilowatts. Okay, as you can see, the temperatures are the same as in the problem. Now we move on to the mechanical summary and exchanger diagram section. As you can see, a general schematic is displayed for us. Okay, the first question is, why Stream 3 is displayed like this? This state indicates the presence of redistribution. For clarification, right-click. After right-clicking, layers A, B, and C are visible. Yes, Stream 3 is present in both layer A and layer C. Now, to eliminate redistribution and simplify the design, we need to go to the Program Options section. In the Design Options section, we also enter a Stream Design. Great! In the Permit Redistribution section, we select No for all three streams. Now, by hitting Run again, we return to the Heat Exchanger Geometry section. Great! By doing this, each stream will be in its own layer and the design complexity will be reduced. Note that in this video, we don't intend to teach all the details, just to demonstrate our ability to solve various projects in the oil and gas field. It should be noted that this geometry is not our desired geometry yet, and many experiences of using the software have not been discussed. In fact, other constraints, such as manufacturing constraints, have not been examined. For example, we have not yet specified what type of fins to use. In fact, the software itself has used its proposed fins, which may not be available for our manufacturer. With this video, we wanted to show that we have the capability to perform various projects in the oil and gas sector. Thank you for your attention. We look forward to your projects.